Now we are going to go a little bit away from an academic, still it is the fundamental basis, but we go out from the academic uh, 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 methodologies of solving the fluid mechanics to applications. The full sessions, which is before regarding the applications, was covering the fluid mechanics itself. Now we are going to check the fluid machinery, or when we have moving plates, like before we was having moving plate, but it's parallel, etc. Like here, and we used Navier-Stokes, for example, a moving plate, Navier-Stokes, and when we have potential flow, we calculate the force for the pipe, if we remember, and for Reynolds transport theory, we used it for the closed or with a system, the control volume or controls the closed system or open system. And we discuss even the compressible flow and the boundary layers modeling. Now we need to check what is the applications. Some application with respect with all the before, but an additional information related to application itself. First, first example. For the fluid machinery, when we have a moving plate, imagine it is theoretical imagination. There is no any equipment which is having such condition. However, imagine that you have a moving plate like this, and there is a velocity hitting the plate and diverting, then the velocity run away or gone from the plate, and the plate is moving with a constant or with a velocity in x direction. So all our fluid machinery, it is a rotational machines like pumps, turbines, compressors, etc., fans, blowers. Okay, but imagine for simplicity, then after we'll go much deeper next one. So imagine that as you are having a V1 hitting the plate and the plate moving at you by logic, relative velocity, which is mean this velocity minus this velocity, but the x component of this velocity minus this velocity will be what? Will be the x component of the relative velocity to the plate. Simple. And the y component of this velocity, and because the plate is not moving in y direction, so the y component of this velocity is the flow velocity, and also it is the vertical component of the relative velocity to the plate. Relative velocity in x, relative velocity in y, so you will get the total relative velocity in the plate. So if you have a tiny person standing here and checking what is the velocity, he will find there is a flow going like this, with this direction, with this magnitude. And if somebody outside, he can see the big velocity. Okay? Okay. Same concept when you have shooting velocity outside as V2. The shooting velocity is going to be outside. However, if there is a tiny man standing here, he will find a relative velocity shooting with the same curvature of the plate, like here with the same curvature of the plate as a relative. And he knows, or you knows, that is the relative velocity. It is taking in account, or removing in account the u. So remove u from this one, you will get the velocity actual, which is coming out. And this is vertical velocity, which is equal to vertical component of V2 or vertical component of VR. And this is the horizontal component, and this is U. Okay, the horizontal component of V and the horizontal component of V, which is mean how much the actual velocity was having in x direction, which is in the rotation, or it is a moving flow, and the actual velocity in the x direction. The difference between these two is how much kinetic energy has been lost actually from the flow, which is translated to a power to the plate, or an energy transferred to a plate. Okay, let's do it in equation. From here we know that is x component of the velocity v1 is, we will name it whirling velocity or tangential velocity. Some textbooks using whirling velocity and some textbooks using tangential velocity. Okay, and here we know this line is what? The whirling velocity. It is u plus the horizontal component of vr. vr, we know its direction or relative velocity. It is always at the same curvature of the plate. So if I know what is the curvature of the plate angle, so I will know what is the x component, and from VR I can calculate VW. Bear with me. So this is beta and this is beta, beta in, beta out. Okay. 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 So let's put it. This is our equations. However, this is what we discuss. This is the whirling velocity or tangent velocity. It is equal to u plus relative velocity cosine beta, or and whirling velocity v2 cosine beta. Same concept, but this one will be minus u. You can see this is full. This is a whirling velocity, and this is minus u. Okay. Fx of the force transmitted to x, we know it from before and etc. It is the mass flow rate multiplied by delta v, the velocity difference, plus the pressure differences multiplied by the area. Assume there is no pressure differences now, but if we have in nozzles and air, okay, but it is mass m dot multiplied by delta velocity. What is the delta velocity we are talking about? It is if you are a one person standing outside or a one person standing on the plate. No, you are going to check if you are the plate. If you are the plate and you're already moving in your direction, so you need to check the change in the x component relatively to the plate. Clear? Clear. So I need this one only, and I need this one only. Okay. So it will be minus relative velocity 2 cosine beta 2 minus relative velocity 1 cosine beta 1. Why it is minus and minus? I know it is delta, so this minus I know it. Why here there is minus? It's simple. You see this direction, so its direction in here, and you see this direction, it is reverse the direction, so it is go against x in the opposite direction, so it is a minus. So v2 minus v1, imagine if this plate is straight like this, it will be not minus, but because it changes the direction, so it will be minus relative velocity cosine beta 2 minus. Okay, we know from this definition that is this one is equal this one plus this one, and the same concept. If you start to put the numbers, you will find that if x equal mass flow rate multiplied by the whirling velocity 1 plus the whirling velocity 2. Okay, this is how we are deriving all of this. Whirling velocity is the x component of complete v, and which already discussed by logic. If I am outside the plate, I know I don't care what is happening inside. I know that is I have velocity x was big, velocity x is small, and if it is same direction, so it is minus. If it is an opposite direction, so it will be plus. And this is the force which I have, which is the first equation. Second equation, we know that is the force uh, uh, we know that is so we know that is the energy which is going to be distributed as a kilowatt as a power. It is force by distance divided by time, or force by u, the velocity of the plate. So the power which is generated here to the plate is m dot whirling velocity 1 plus whirling velocity multiplied by u. We know that is the energy divided by mg, if you remember, uh, equal to head. So head is energy divided by mg, which is equal to divided by g. So the head which is giving, so you are giving a head to that one. To, for example, if this is turbine, you are giving a head to the turbine with equal to v1 v whirling velocity 1 plus whirling velocity 2 multiplied by the moving u divided by g. Okay. This equation will return it last after we finish all the machinery, not now. So let's have the first actual application. Built-on turbine. I know we are going to CFD, we're not going to discuss, or we're not going to make any simulation for. Maybe we'll do, but uh, it is helping us to understand when you're dealing with the bumps, when you're dealing with any moving plates, when you're dealing any flow streams hitting something. For example, a flow stream hitting a wall, hitting a building, wind would hit all of this. You need to check what is the velocities in, velocities out, forces, and head and energy and power. In case if you have fans, for example, and you know that is you're doing a CFD and you have a exhaust fan and the fan having a small having a wind in front of the exhaust fan at the roof. So you can do this calculation to get what is the head adverse by knowing the blade angle. No need to draw the fan itself and to simulate the fan while you are concentrating to simulate the building. You get my point. So this is the point which is analysis you need to do, even manually or whatever. Okay. Built-on turbine. Built-on turbine is very simple. If you have a big tank and the tank at the end of the tank there is a nozzle and it is in open atmosphere, there is this jet will happen. Jet will hit the plate here, then the plate start to rotate like this. Then another plate will come, hit, another plate will come, hit, another plate will come, hit. So it is moving in u, and u equal to rotating velocity multiplied by the radius. However, it is the same concept we can identify like what we done here. We need to draw the velocity diagram. So what is the velocity diagram? The velocity diagram, which is v coming here, based on this, so v1, the actual velocity or absolute velocity, it is equal to relative velocity. And there is no x and y component, all are in x component. See, it is all in x component. So from it, v1 equal relative velocity minus r, of course r, minus r, because is this one and this one is running, and we know that is this one minus this one, so it is u, like we done here. We know this one is hitting like this, and this is the x component, and we know this one is u. This one minus the x component is the x component of vr, but because we don't have vr x component, this is all in x direction, so v1 equal vr minus u equal whirling velocity 1. The whirling velocity is the x component of v. Okay. And we know that here, the distance between here and here is very neglectable when you know that is the Pelton turbine, the center is here when it's rotated like this. So this distance, and the radius here, is almost equal this radius. So we can assume that is u here equal u here. It is very valid assumption. So we know that u1 equal u2 equal u. But now here we know that is the velocity going to out of the plate always with the same curvature of the plate. But if this one is going in this direction and u is going in this direction, so go like this. So this is the v. The x component of v is whirling velocity, and the vertical component is the flow velocity. Flow velocity, which is mean the velocity is the velocity here exactly. Okay, okay. Now we draw the diagram, of course, by knowing the plate angle, etc. You can, it is a phasor course and triangle calculations. Okay. Okay, there is another point which in just a recall, it is not a big deal, but a recall that is if we know the height here and we know there is a V, so an H friction going to be loss here. So the net loss, or so the net head, which is reaching till here, the net head is what? Is the hydraulic head or the ground head minus the friction itself. Okay, and the velocity here is equal to CV, which is constant for the nozzle, multiplied by root of 2g h net. So how much head I have here, how much the it is orifice, it is like an orifice or a nozzle now. So it is velocity, it is, if this one is not there, we know it is root 2g h, but because there is a coefficient for the nozzle, so it is CV. Okay, okay, okay. Based from the before, we know that is force equal m dot whirling velocity minus whirling velocity. But before here, it was whirling velocity plus whirling velocity. Why? Because it was enter like this, and this is the whirling velocity, and it was going out like this, and this is the whirling velocity. Now it is enter like this, it is going out like this. Same concept. So it is the whirling velocity 1, sorry, 2 minus whirling velocity 1. Okay. And the energy also as well, it is, we know that the energy is torque multiplied by omega, and omega is U divided by R, and so torque equal force multiplied by radius. So we can write that the power is equal to, or equal to m dot whirling velocity 2 multiplied by u2. This is u, and whirling velocity 1 multiplied by u1, because here is r and the omega, so r by r remaining only u, because we know that is u. Of course, if the u not equal, we need to keep it in this form, because we know u is equal, so put u outside, so it is m dot u whirling velocity 2 minus whirling velocity 1, and the head divided by m dot g, so the head is u divided by g whirling as m dot equal q by the way. Eta Belton turbine. Okay, if somebody told you we need to check without naming it even Belton turbine, but what is efficiency of this one? The efficiency of this one is very simple, is how much energy I really got, which is from this equation, divided how much energy I can take it from the nozzle, which is half O Q V1 squared. Of course, you tell me both is equal. No, this one, it is the energy coming from the nozzle. Of course, if you need to define this energy coming from any nozzle, or from any power is coming from any, uh, it is kinetic energy, by the way. So kinetic energy, we just said, rho q, it is the m dots half m dot v1 square. It is the kinetic energy, total kinetic energy. What is the velocity here? And the velocity here, we can get it from the this equation. Then we will check what is the blade curvature, and because the velocity here will never be equal 0, so of course it will be losses. That means there should be losses, which is eta Belton turbine. This is very simple, but it is good for us to understand a lot of points. Of course, because here it is pressure at atmospheric pressure, here is pressure at atmospheric pressure, it is way easy to deal with such application. Okay. Later on, we will find when you go to pumps or Kaplan turbine or pumps, centrifugal pumps or axial compressors. This idea will become more complicated more and more, but it's good to start up. Okay, now we're going to have the Francis turbine. Okay, let's return back. Francis turbine. Francis turbine. One second to just to understand how it's shaped. Francis turbine. Francis turbine. It is exactly like this. Exactly like this. Water come in the middle. Then it is rotating an impeller, and the impeller giving uh, the water to. Uh, by the way, the impeller is named as runner, and then it giving to guiding or a guide vein, and then a helical or a volute shape of casing, which is this shape of casing. What is happening? See, first we need to understand what is the philosophies to make the velocity analysis and the velocity diagram. So what is happening? We have a high pressure, low velocity here, high head. We are converting this head by any method or other to a kinetic energy. Okay? And this kinetic energy, I need to absorb it as max as possible. Okay? So if we just return back to here, if you can see, the outlet is way big, and the inlet, which is water, will rotate like this. Let's go check one clear section. Sorry, the water enter from here, not from the middle. So what is happening? When you have an, I was discussing about the pump. By the way, the pump, centrifugal pump, is the opposite case of this one, but without the guiding vanes. So you have a very large case or violet case or helical case, which is big, then getting to be reduced. So the velocity get increase. Then the velocity will have a very high speed. So you're converting the pressure by reducing the gap to make more velocity. Then if you can see the guiding vanes start to push the water here, then the water will rotate that impeller, then it is go out from the middle. This is how it is running, and this is how it is built. We are going to check the heads now after, but from the velocity diagram for the plate instead for the runners, because here where is the power we are getting? Here is the power. Here whatever we are arranging the flow with a condition to take from it the maximum power. Okay. Yet when it is reached here, this is actual power absorption for the turbine. So we know that velocity is going to hit the impeller, and the relative velocity is with the same curvature of the impeller, same what we discussed before. So the velocity, it is the whirling velocity u. So this one is the horizontal velocity for relative velocity, and this is the flow velocity. Very simple, like before. Okay. Then the velocity will start to go out as a relative velocity. It will go out from here as a relative velocity. Yes, agreed. And we know that there is a u velocity, a u, but take care because this one is rotating, and this radius is different So, and it's not like in the Pelton turbine, which is the radius. So this radius and this radius, it is almost the same. No, this radius and this radius is very near to the axis, so which is mean it is different. So u here is different than u here for a certain uh, rotation speed. So we will have here u1 and we will have here u2. Flow velocity always equal flow velocity, like what we have in here. v1 and the flow velocity it is equal for sure as a flow velocity because uh, this is which has been gone out. So flow velocity is equal flow velocity. So flow velocity 1 equal flow velocity 2, which is equal to the velocity 2 itself. So velocity 2, why we kept it vertically from here? Because we said that it is going here in this point downward. So the velocity component either it will be in x or y, right? The plate is designed to keep all the velocities in the x, which is in the vertical component. So imagine this one rotating. So it is always going in this component, which is mean there is no x and y, which is mean there is almost no whirling velocity in this, which is mean no rotation almost. Imagine like this plate is fixed in the center. Imagine it like this. So it's not rotating. That's mean there is no whirling velocity. Of course it is rotating, but eh, when it's the velocity going like this exactly to that center, which is mean there is no component for this velocity vertical on the rotation. Got it? Again, bent. Imagine this is the plate and this is the center of rotation. We agreed that the whirling velocity is what? The whirling velocity is the velocity vertical to the rotation. Mhm. When it is moving like this, the whirling velocity, what is the whirling velocity? It is the velocity which is on the rotation itself. But because the flow is going exactly to here, which is exactly like this, so and it is rotating like this, so there is no effect or there is no component of the exit velocity affecting the rotation itself, which is mean there is no whirling velocity at the exit, which is mean v2 is just vertical on the rotation itself, which is v2 equals 0. Apply the number. We know this energy divided by m dot equal whirling velocity 2. We know it is 0 minus whirling velocity 1. So it is equal whirling velocity 1. Of course, minus, which is mean you're taking ahead. So you're removing energy from the water because it is a turbine. So it will be in minus. But it's okay if you keep the minus, keep the minus. But if you remove the minus, you need to know you're taking energy from or taking power from the water. Okay, and the head is divided m dot divided this. Sorry, or rho g divided as we agreed before. Head equal energy or power divided by m dot g, and because we know this one is power divided by m dot, so head is this one divided by g, which is v whirling 1 multiplied by u1 divided by g, and this is the net head. What is the net head? This is whatever net head we have, this is whatever we are going to get. Easy. Okay, so okay, what is net head? If I have a tank, same concept, there will be losses till the water will reach they'll here, which is the friction losses. Okay, so the ground head minus the losses will become h net. Yes, but no. See, this head is the available head. This is the losses, and there is also a losses. What is this losses? Because we are not like here, which is atmospheric pressure, atmospheric pressure. No, here we are in continuous flow in a turbine, then a pipe, which is named draft tube. So there is a velocity going to be escaped. Otherwise, if the velocity didn't escape here, which is mean h net reach to this point, which is mean the velocity is zero, which is mean flow is zero, there is no power extract. So by any method, we need to let it go. We need to let the velocity go with some velocity to keep the flow rate running to get the power. But we are trying to keep this velocity as low as possible. So how to keep this velocity as low as possible? In the draft tube, try to keep it as bigger diameter. That's it. Okay. Okay. And head is normal. Huh? Head is v square over 2g. V square exit over 2g. Okay. V square exit is what? Is v2. Okay. Okay. So now we know h net, which is equal to this one, and we know what is the maximum head we can get is h net plus this head, which is v exit over 2g, so or v2 over 2g. So put the numbers. So eta of the turbine is whatever we get from here plus whatever we get from here plus this head. Of course, we're using energies, so write it v square over 2. Energy by mass flow rate. Of course, mass flow rate is kinetic energy. If you're going to use head, no problem, but you will use head plus v square over v2 over 2g. Okay. Okay. So this one is the efficiency of the turbine. But note, we don't have only these losses. We have another losses. You remember regarding the assumption that is the velocity is going here direct to the center. Imagine that this angle is a little bit not right. So here a velocity or the whirling velocity here is not zero. And this velocity started to be slipped like this. So this assumption will be inaccurate. Okay, but we didn't assume it now. Okay. Also, there is another losses. The outlet here, due to we have a draft tube, the outlet here itself, there is some frictions going to happen in the draft tube due to viscosity, or maybe the draft tube is bended or whatever. So there is a losses also in the draft tube. We need to take it in account because these losses act as a resistance for the flow to go, resistance to the flow to go, less flow, etc. Okay, so due to the viscosity and regarding the boundary layer of, there is some losses will be, which is related to the draft tube loss. Usually the draft tube loss needed to be maximum diverging with 8 degrees. We know that is when we keep it more diverged, it is good. That is less velocity, more power we're going to get. But we cannot keep it more. Why? Because if we keep the draft tube more diverging angle, separation going to happen, which is you remember the separation itself, which is going to happen when we have a diverging flow. So, and the pressure here, it is higher than this pressure, then a separation going and vortices going to happen, which is more and more losses going to be. Okay. So usually we keep it maximum at 8. Okay. Now we have a specific speed for the turbine. We already discussed it in the last session. What is the specific speed for any turbine? It is how much omega, which is the rotational speed, multiplied by power to half, divided by rho power to half, multiplied by h gh power 5 over 4. And it is just from by theorem, by the way. And there is another terms. Maybe we'll do simulation. Somebody will tell you, or the client will tell you, okay, what is the degree of reaction? I need to calculate it. What is the degree of action? Its definition is very simple. This is a change due to the water divided by the total change in the energy. Okay, so change in energy due to the water. Change in energy due to the water is this equation, by the way. This equation, okay, which is this one. This is a change in the energy. That's it, due to water. Because there's no, this one is only for the water. Divided by what? Divided by the total change in the energy. What is the total change of the energy? From the inlet, the guiding vanes, so all of this change, okay? It is just a definition, just to be in the picture, to calculate it later on. Okay. Now there is one definition you need to understand, which is named the setting. What is mean by setting? Setting is where we can keep the turbine. For example, you will tell me, okay, I am going to keep the turbine as low as possible. Yes. Or somebody will tell you, okay, I will keep the turbine a little bit higher or a little bit lower. Let's discuss each term and what is the advantage, disadvantage for it. We know, we know, while we are keeping these turbines here, when you have a column of the water start to create here a height, it will create like a suction pressure, which is will give you more power. You will tell me, how do you know it? Apply the control volume. Control Reynolds transport theory, control volume, apply it please. So point number one, point number two, point number one, point number two, B1 over OG V1 square Z1 equal this term at the atmosphere, okay? B atmosphere, which is outside, rho g v2 2g, okay? Okay, we know that is v2, which is going to the tank itself, is way less than v1, which is a very high speed. And z2, we will assume it is our data, so it is equal 0. And v2 will assume it is equal 0. And because of a2 is way bigger than a1, so that's why v2 is equal 0, by the way. So we can say that is the pressure 1 over rho g, this is bye equal to v1 squared over 2g plus z1 plus h friction. This is clear. Pressure at 1. Here, by the way, here it will be minus. It will go on the other side with minus. And this will be in minus, by the way. And here is the h friction. So this will be minus. I don't know why it is. I don't know. I will add it. Okay. So from this, more Z, which is mean we are giving more Z, which is mean we are giving this turbine more height. What it will give you us? Less pressure at 1, which is less pressure here. Less pressure here, more and more pressure difference, which is more and more power. So length of the draft tube, we need it to be, or the height to be as max as possible as we want. Also, when V1 uh, started to be from this equation, by the way, if more this one, less this one, also if more V1 will create less V1, but it is not in our benefit because if more V1 will create yes less V1, but still more V1 is losses itself. V1 it is the outlet from the turbine. So no, we don't want to change or play in V1. We just want to play on Z, only Z. So the height of the turbine from the surface of the water, when it is way higher, it is better and better to create يعني even if the water is here, if the water is here, but the draft tube it is thrown to atmosphere, but the draft tube is way down. So let's keep Z at infinity. But if we kept Z1 as infinity, which means the height of the draft tube or the height of the turbine is big, more big, will give us less and less and less pressure, which is can reach to the cavitation. So there is a limitation. Yes, we can do it, but till the limitation of the cavitation. Okay, okay. This is a Francis turbine, by the way. The other one is the Kaplan turbine. It is the same Francis turbine. It is like a pump, but this one is like a fan. Okay, so the water is coming here, axial, and the turbine as a fan is rotating, same draft tube. By the way, the draft tube location of setting is the same concept. And the velocity diagram, we can write it like this because we know that is the flow going like this and going out. So it is go in the plate like this, go out like this. So we know that is relative velocity is vertical, but v it it is not vertical. So we have a whirling velocity, and because we know that for a certain slice of the water which is going in and out at the same radius. So you know that is u in and u out is constant, which is so this one is this one, and this is relative velocity. It is the same concept, by the way, but because we know that is Vf should be very, very vertical, it's because it is vertical, Vf is vertical, and Vf2 is vertical and is equal Vf1, and it is equal to V2 because it is going out of the same direction of V2. It is the same like here. So in Francis turbine, V2 is equal to Vf flow because of the plate is throwing at the center. Here also Vf equal to V2 because also the way of exit it is perpendicular on the rotation, so V2 equal Vf also as well. Of course Vf1 equal Vf2, and because Vf1 is vertical and I know that this Vf1 is the vertical component of V, so I know like this is the whirling velocity. I know that is u is in this direction, so and V will be relative velocity will be like this. So this plate will be like this. Okay, okay. So energy or power divided by mass, flow rate is whirling minus whirling. We know that the whirling velocity we know that the whirling velocity 2 is equal 0 because v2 is vertical. Same concept, it will be minus whirling velocity 1. Of course, minus, which is mean we're taking power, you can move the minus from the, it's okay. Eta is the same concept, that is, there is a losses in the draft tube. It's not losses as a friction, but losses due to an exit velocity. And we know that there is a losses in the friction till the turbine, so H net, same concept. And same, which is velocity whirling multiplied by U and H whirling. It is the same equations, by the way. Even the construction of the turbine has been changed, but to calculate the velocities, you can relate to the velocity diagram. But when you get the velocity diagram, the all other equations is the same. The remaining is about the pumps.